All right. So we are going to be talking about phase shift, which is horizontal translation and also vertical translation in this video. But before we do that, I did want to work out just a quick example to kind of start us off. Now you might notice I've got this weird thing in front of me right now. I'm going to try treating my phone as a document cam to see if I can't work out an example down here. So I'm going to switch my view so that you see this as the main video. Okay. So we're going to try and think about what information we can get from y equals 2 sine of 4x, and also see if we can sketch a rough, by hand, sketch of this graph. All right, so the first thing we're going to think about is we're thinking about this in terms of translations. So I want to think about what the basic graph of just sine looks like. So the sine graph. Remember the things we know about the sine graph. The sine graph has an amplitude of 1, meaning it goes between -1 and 1. It has a period of 2 pi. And remember, the important thing to differentiate sine and cosine is sine is going to start at 0, 0, go up, come back down. And that right there is going to be one full wave or one full period. So this is going to be 2 pi. And then that pattern is going to continue in both directions. All right, so this is our untransformed sine graph. It's not great, but it's good enough. Now let's look at what information we can get from our equation y equals 2 sine of 4x. Well, we've got this multiplier out here. This is representing a vertical stretch or shrink. In this case, this is a vertical stretch by a factor of 2. Which means we've taken this graph and stretched it to make it taller. Now, what is that going to impact? That's going to impact our amplitude. Now, the original amplitude of our sine graph, sine went between -1 and 1, so it had an amplitude of 1. We have stretched this by a factor of 2, which means our new amplitude is 2. Okay, all right, what else can we get from this? Well, this multiplier inside of the sine function, this is going to be a horizontal stretch or shrink. Okay. And this is really going to impact our period. Okay. Now remember, this is going to represent a horizontal shrink. In other words, it's going to compress our period down. Or another way of thinking about this is we're going to have more waves in a regular 2 pi period than we would. Okay, so this is a horizontal shrink. It tells me that there's going to be 4 waves in our normal 2 pi period. And this is going to let us get our period. Okay, so remember, to get the period, oops, I can spell, not really. We take the original period of the sine function, which was 2 pi, and we divide by that multiplicative factor there. So 2 pi divided by 4 is equal to pi over 2. So our new period is going to be pi over 2. That means our sine graph is going to repeat every pi over 2 units. All right, so let's see if we can put this into a basic graph. Okay. All right, so I still know that my sine graph is going to start at 0, 0 because I haven't done any horizontal shifting or vertical shifting. We're going to do that next in this kind of video. Okay, but what I have done, right, is I've made my amplitude bigger. So as opposed to going up 1 and down 1, my waves are now going to go up to 2 and down all the way to -2. The other thing that I've done is I know that my period, as opposed to being 2 pi, is now pi over 2. So if we think about, originally we had 2 pi out here. Well, between 0 and 2 pi is pi, and between pi and 0 is pi over 2. So we're now going to fit, I should have made this graph bigger as usual, but we're now going to fit one full sine wave right inside here between 0 and pi over 2. Okay, I'm going to go ahead and fill in this little tick mark here between pi and 2 pi would be 3 pi over 2. All right, so I need to draw one full sine wave between 0 and pi over 2 because that's our period. And I know my sine wave needs to go all the way up to 2 and all the way back down to -2, come back up, and there's one full period. And then it's going to repeat that. Up to 2, down to -2, up to 2, down to -2, up to 2, down to -2. Okay, so there is an example of our shifted graph. Notice what I said earlier. I said in our original period, which was 0 to 2 pi, this horizontal shrink here really means that I now have 4 complete sine waves in what used to be my single period. All right, I'm going to pause real quick, and then we're going to look at this graph on Desmos just to make sure we agree with what we did here, and then we'll continue on. All right, so hopefully now you see Desmos, and I've got the sine graph up there in purple. So that's our original sine graph. That's the same thing that I have in purple over here, just kind of a different scale. And remember, we said that this has an amplitude of 1, so it goes up to 1 and down to -1, and a period of 2 pi. So we get one full repetition of the sine wave between 0 and 2 pi. Now let's look at 2 sine of 4x. We said that this was going to change our amplitude, and it certainly did. Our amplitude now goes between 2 and -2. So, sorry, our wave goes between -2 and 2, so our amplitude is 2. Then we said that it was going to make our period pi over 2. And look, right here between 0 and pi over 2, we have one full wave. We also said that that 4, we could interpret it as meaning there would be 4 full waves in a regular period. And I sure see 1, 2, 3, 4 full waves in that regular period. So I think we did pretty good with our sketch there. All right, I'm going to pause again and move the cat and also get ready for the next part of this video. All right, for the rest of this video, we're going to be talking about reflections and horizontal and vertical shifts. So before we do this with trig functions, I just want to do a quick review of this with just regular kind of functions from algebra. So we talked about this a little bit, but if we have the basic x² function, we talked about stretching it horizontally, or we talked about stretching it vertically. You can't really stretch this one horizontally. It becomes the same thing as a vertical stretch. But the other thing I want to talk about is horizontal and vertical shifts, okay? So if I have x² and I change that to x minus 3 quantity squared, notice that that moves my function 3 units to the right. If I do x plus 3 quantity squared, that moves my function 3 units to the left. By contrast, if I do x squared minus 3, that moves my function 3 units down, and x² plus 3 moves my function 3 units up. So horizontal and vertical shifts depend on adding and subtracting, and it's going to change. If it's a horizontal shift, I'm adding or subtracting inside with my variable x. If it's a vertical change, I'm adding or subtracting outside, okay? Now we can combine those together. So if I have something like x plus 2 quantity squared, oh my goodness, minus 5, notice that this is a horizontal shift left 2, we've gone left 2, and a vertical shift down 5. So we can combine these things together, okay? The last thing I want to talk about with this is what happens when we throw a negative out in front. A negative is an x-axis reflection, meaning it flips our function upside down. Okay? So I throw a negative in front of this guy, it flips our function upside down. So negatives out in front flip our function upside down. And there's one other way we can flip our function. We can do x-axis reflections, but we can also do y-axis reflections. Now in the case of x², a y-axis reflection doesn't do anything because this thing is symmetric about the y-axis. It's also known as being even. So let's look at one other function. Let's look at the square root of x function, okay? Now we can do an x-axis reflection on this by putting a negative out in front. That flips our function over the x-axis. But in this case, we can also reflect over the y-axis by putting a negative inside with our function. So that's acting as an x-axis reflection. We're going to be able to reflect our functions, our sines and cosines, our trig functions across the x-axis, across the y-axis, and we're also going to be able to move them vertically by adding or subtracting outside of our kind of trig function argument, and we're also going to be able to move them horizontally by adding or subtracting inside of our trig function argument, and that horizontal shift is also known as a phase change. All right, so let's take a look. So let's work with our sine function. So here's our sine of x function, has period of 2 pi, amplitude of 1. We know how to change the period and the amplitude. Changing the amplitude means I multiply by something in front. To change the period, I multiply inside with my x, okay? Those also we can also think of those as representing vertical stretches and shrinks and horizontal stretches and shrinks. All right, so now we want to think about how we can reflect this across the x-axis and across the y-axis, and also move this horizontally and vertically. All right, let's talk about those x and y-axis reflections first. Well, when we do an x-axis reflection, we put a negative out in front. So I'm going to put a negative out in front, and we're going to see how this changes. Does that, oops, go back and forth all the time. It sure looks like that's an x-axis reflection. It might be a little easier with this guy to put two different functions up. So in blue is our original sine function. In purple is our negative sine of x function. And notice that those are reflections of each other across the x-axis. All right. Y-axis reflection means I put a negative inside with the x. So sine of negative x. So it's, again, a little bit harder to see, especially when I don't have a good view there. Let's do this. Okay. So let's look. Here's sine of negative x, sine of x. And again, it might be a little bit easier for us if we actually put both of these up at the same time. So when I put both of them up, you can see that sine of x and sine of negative x are reflections across the y-axis. All right. So now let's talk about horizontal and vertical shift. Well, remember that a vertical shift is when I add or subtract something outside of my function. So just for a minute, think about what will happen when I take sine of x and I add 2. What is that going to do to my function? Let's see. That takes my function and shifts it 2 units up. What if we do sine of x minus 2? Well, that takes our function and shifts it down 2 units, okay? So adding or subtracting outside of our function is going to move our function vertically. Now, one thing that's a little interesting about sine and cosine functions is often, as opposed to doing this in back, so sine of x plus 2, we do it in front. In other words, we switch the order and we do 2 plus sine of x. Notice that that's the same thing. That's still adding 2 to my function. If I wanted to shift my function down, I would have sine of x, and I would have to take away 2. So I would add negative 2, which is the same thing as subtracting 2. Notice that moves my function down 2. All right. So now, horizontal shifts, these are also known as phase shifts, happen inside with the x. So for example, if I want to shift this function over 2, I would add 2 inside with my function. Now remember, horizontal shifts work almost backwards. So adding 2 is going to shift my function 2 to the left. So it took this point and shifted it 1, 2 units to the left. Okay. If I were to subtract 2, it would shift my function 1, 2 units to the right. Now, oftentimes we're not shifting these or thinking of phase shifts in terms of numbers like 1, 2, 3. Rather, we're thinking of phase shifts in terms of pi over 4, pi over 2, 3 pi over 2, in terms of radians, okay? So let's see what would happen if I shifted my function like this. So I have sine of x minus pi over 2. Well, sine of x minus pi over 2 means a horizontal shift to the right of pi over 2 units. So I would expect to see this graph picked up and shifted pi over 2 units. Let's see if that's the case. Yep, I've just shifted this graph to the left, to the right, excuse me, I know left and right, to the right, pi over 2 units. Let's do another one. How about this guy? Well, this looks like a horizontal shift left of 3 pi over 2 units. So I'd expect to see this shifted to the left by 3 pi over 2 units. So in other words, it's taken this and moved it all the way over here. So this 0.00 is now over here at negative 3 pi over 2, 0. Now, here's the fun thing. We can combine all of these different elements at once. Okay? So let's start with just a vertical shift and a horizontal shift. So let's say I want to shift this up 1. Okay, so that's an up shift or a vertical shift up 1. And I also want to shift this to the left. That's plus, let's say pi over 2. So I would expect that this graph is going to look like this graph shifted up 1 and to the left pi over 2. Let's see if it does. So this point 0, 0, has it gone up 1 and over pi over 2? It sure has. Okay, let's try another one. Let's throw in a reflection as well. So let's shift this down 3, and then let's reflect this across the x-axis. And let's go to the right by pi. So down 3, x-axis reflection, to the right pi. So I expect to see this curve flipped upside down, shifted down 3, and to the right pi over 2. So let's see. Upside down, it's hard to tell because of this phase shift thing, huh? So let's do these things one at a time. So negative sign of x is going to be our reflection. So we reflected that. Now let's move that down 3. So there's our reflection moved down 3. And now let's move this to the left pi units. There we go. Awesome. Okay, so I'm going to end this video here. We've looked at x-axis reflections, y-axis reflections. We've looked at horizontal shifts, this way, horizontal shifts and vertical shifts. Okay. We will also do some where we look at all of these all together. So I'm going to do another video.